Hello, hello.
G'day everyone, can you hear us?
Yep.
Sweet.
I can see one familiar face.
I think Chris Akiki is like everywhere. Do you clone yourself?
Oh, thank you for unmuting me. For a second, I thought you were not letting me speak.
Wow, you have like a full podcast to set up.
I do. I'm also wearing my Rocket hoodie, sweatshirt thingy, because I thought Leandro would have his Rocket in the background, and now I just look silly. Where are you guys?
In our co-working space.
Oh, very cool. Is that where we always see the Christmas store? Somewhere in some corner?
Yes, that's like in the meeting room, but today everybody left, so we can use the whole space.
Very cool.
I guess we can just wait a couple of minutes for people to join. Vivi, can you speak?
Yes, can you hear me?
Yeah, because
Okay, perfect. I am facing troubles with my video for some reason, so I'm trying to figure that out. Wait, okay, it works.
Oh, cool t-shirt.
Oh yeah, that's I just unpacked it and just wore it.
What time is it now for you?
So it's 9:30 in the evening.
Well, thanks for taking the time.
No, it's fine. I'm anyway working in European time zone this entire week and next, so it's all chill.
Hey Maria, how's it going?
Should I unmute?
Oh, hi. Can you hear me?
Yeah, nice to see you.
Yeah, nice. Yeah, everything is going nice. I've just like finished working. Yeah, I'm really looking forward to this reading session.
You have a copy of the book, right?
Yeah.
Cool. So you're probably one of the experts here. You probably know more about it than we do.
Yeah, sure, more than the writers.
Well, to be honest, I kind of forgot it. It's like when you finish your thesis, it's just like cram and then submit and then you forget. Sorry for anyone who came here expecting to learn something, deep and meaningful about Transformers from us.
Was there a particular chapter that just did not want to get written? Because I struggle with that sometimes in like paper sections, and it'd be cool to learn how giving birth to a book.
What was it?
I think it's more painful than actual birth. No, but I think the one that took by far the longest was, I think, the pre-training from scratch section, because like a lot of the transformers and accelerate API was like being developed to work with that chapter. So it was a tight call to get it in time. And also, I think it was probably twice as long at the beginning.
Yeah, I think another chapter that was really tough to write, not implement, was the Transformers Anatomy one. And like figuring out how you introduce the concepts at the right points in the book, because you don't want to like overwhelm people in chapter one. And I remember like Leandro and I shared that chapter back and forth probably times before we found roughly what we wanted to do. Because I had this crazy ambition to train the transformer like from scratch in that chapter, like as in not pre-training, but just train an encoder to do classification. But then yeah, it was just getting too crazy, and yeah, it was pain.
Super exciting. You mentioned that the training from scratch chapter was happening as the code was being developed. So I'd imagine it was a great stress test for the people developing.
Yeah, I think it was a lot of stress for both sides. Like, I think the two things that were implemented for that chapter was like in data sets, there's now the feature that you can stream data. And that was being built while we were using it.
Oh.
And Accelerate was also pretty new. And I think that was one of the first projects where we like trained a pretty large model for a long time with Accelerate. And there were a lot of fixes along the way, which is a good thing.
Yeah, that was also the case for big science. A lot of stress tests for like some weird, like obscure part of the library that just failed at the scale we were trying to do things at. And it's super interesting to see how like these projects flow back into open source.
Record.
It's recording.
That's sweet.
Yeah, we got the notification as soon as we joined that it was being recorded.
My brother is now watching you.
Yes, it sounds a bit like you actually want to start a podcast. We should continue with your questions.
What are you drinking, by the way? Was that coffee at 6 in the evening?
I'm drinking beer.
I'm drinking coffee.
Beer makes sense. Coffee does not.
Yeah, I mean, it depends on how like fun you want this session to become.
See, I'm clearly the fun one out of the two of us.
Yeah.
We didn't need beverages to know that.
Thanks. Yeah, I guess we're now 5 minutes in, so we could as well get started formally. Welcome everyone to the reading group. It's been a while since the book has been out, but we thought like there has been some requests to like go through the book together in some form, be it like a reading group or something similar. And so we thought it's better late than never. And this is our first session. Today, Louis, Vivi, and me are here to go through a chapter. Maybe we can just start with like a brief introduction. My name is Leandro. I'm a machine learning engineer in the open source team at Hugging Face. I've joined Hugging Face not that long after we finished writing the book. In a sense, like working on the book was the longest interview I ever did. Now since a little bit more than a year, I'm in the open source team. You want to introduce yourself?
So yeah, good day everyone. My name is Louis, and according to Clip, I am a close-up of a person wearing a white shirt who happens to also be Australian, but has an extremely long forehead. So if you haven't seen this, check out the Clip interrogator, where you can get basically insulted by machine learning models. But more seriously, I'm also an engineer in the open source team at Hugging Face. I work on the transformers and optimal libraries. And it was the same, I've been here for about a year and a half, so roughly similar experience with Leandro just after the book, and then joined. DB, do you want to go next?
I think
you have to unmute him maybe. Because he muted himself.
Well, hello, I'm Weeby. I'm a student researcher at the University of Stuttgart. I basically break all sorts of things when it comes to audio and sometimes text generation. I am also a Hugging Face fellow. And you might have previously been part of my boring audio sessions and so on. I'm looking forward to this journey with you all together. And yeah, thank you so much for being here.
Sounds good. Thanks. So let me briefly talk about organization. The way we want to run this reading group is like as a community. So it shouldn't be just me and Louis and VB talking, but we want anybody to be able to participate. So this week it's us that organized it, but in the following weeks, if you feel like you read a chapter and you want to talk about it, we welcome or almost ask that somebody else like takes over. We're happy to like support, and we will also join the sessions. Maybe not all of us all the time, but at least one of us some of the time. So Lewis and me, we're co-authors of the book. There's also Tom Wolf, who said like he would be interested in joining a few sessions. So what we expect for the session is that before the sessions that you go through the chapters so that we can like summarize the content of the chapter pretty quickly together, and then spend most of the time like on the interesting part, which is like your questions and discussions around the book. So the idea is that we probably present for 10-15 minutes the content of a book chapter, and then the rest of the chapter is dedicated to discussions. We also announced, that's not on that list here, that this reading group should also help people with contributing to open source. This week, we're going to focus mostly on the book, but starting from next week, we're also going to have like some fraction of like the reading group dedicated to learning about how to contribute to open source, how, for example, one can open an issue, create PRs, and interact with the ecosystem. So the timeline is, today is the kickoff session. We're gonna walk through like the very first chapter in the book, which is more very high level chapter. It's not too much code. Next week, not next week, but in 2 weeks, we're gonna do it in like 2-week intervals. We're gonna talk about text classification, which is like the first hands-on chapter. And then after that, essentially, you can decide which chapter you want to look at next. We're going to do some votes. Maybe we take like a sub-selection of all the chapters for the vote, but essentially we are guided by your interest. So if there's a particular chapter that you find interesting, you can vote for it, and then we look at that first. So yeah, I think that's pretty much it. Let me get started with like the very first chapter, which is Hello Transformers. And one thing that that chapter goes through is a little bit like the evolution of Transformers. Like if you start looking at like the Transformers paper, you see like a very complicated diagram, and it might not be so clear how that diagram came to be. It doesn't look like something very like intuitive that you think like anybody could have come up with that. But if we go a little bit like through the evolution steps between different architectures, it becomes a little bit more apparent why Transformers came to be. And so the very first thing that you can see here is like an RNN, so a recurrent neural network. How a recurrent neural network works is that it gets some input T, and then it passes that input through this so-called like RNN cell, and then part of what comes out of that cell is the state that can be used, for example, later on for classification or something. And there's a tiny part that the RNN feeds to itself. And one way to visualize that a little bit more intuitive is if you unroll such an RNN in time. So if you think about an RNN that gets like several inputs, input 1, input 2, input 3, that could be, for example, be words in a text or in a sequence of numbers. So the cell gets like the first input, it generates the first state, and then for the next step, it passes some information to itself. And it does that at each step. So some information always gets passed to itself at the next step until you arrive like at the end of the sequence. And that self-feeding mechanism is what allows the RNN to keep track of things and have kind of like a memory of what happened previously. So at the very end, when you come to state T, the model has like the ability to know what happened at the very first input. So if that's a sentence, it, for example, knows what the subject of a sentence was. And these RNNs are very nice. They've been used for quite a while. If you want to do something like translation, usually you use 2 RNNs for such a tasks. So here we have the example of transformers are great, and in German, transformers sind großartig. And one way you can address this translation problem is by having an encoder block, where essentially your input sequence gets fed through that RNN. And then at the very end, you take like the very last state of that RNN and you feed it to the decoder block, which has like a separate new RNN cell, which is just there to decode that state, which should like kind of capture the meaning of the sentence into the sentence in the new language. That was like the default way to do these things like a couple of years ago. One issue that you have is that everything that you need kind of on the right-hand side needs to be encoded in the state. So if the state doesn't capture all the information that's necessary to come up with like the translation on the right-hand side, then the decoder block has no chance to properly decode that state into the translation. Ideally, you would be able to pass like all the states to the RNN, to the decoder block. But that's also not so easy, because then you have like a lot of information that needs to flow from the left to the right-hand side. So this part in the middle, like that state, that's usually like an information bottleneck for the translation. It didn't take so long that people then came up with like a new way to do that. That's a little bit more efficient. And instead now of just having the last state that gets transferred to the decoder block, you transfer all the states, but I said like just before, that's usually not ideal, because then you need to process all that information. For example, if you want to pass that to the RNN cell on the right-hand side, you would need to like stack the states somehow or average them, which might also lead to like some loss in information. And one way you can do that is by adding an attention mechanism. And the job of the attention mechanism is essentially figuring out which state is important for which step. So if you're, for example, here at the RNN, the second decoding step, and you want to know, you want to decode like the second word, then probably it makes sense to look at the second word in the first sequence. So the attention mechanism could be heavily focusing on that second word. And that's like where the original attention came from. It wasn't in transformers, attention was there already before. And one cool thing that you can do is you can visualize how the attention looks like in such a translation model. So here you can see 2 sentences, one in English and one in French. And it's about like an agreement on the European Economic Area. And you can see the attention is visualized in that matrix. So at each step, you can see to which token in the other language the model attends to. So when you want to translate then the model looks at the first token, agreement is accord, and so on. But one thing that's interesting is like, if you look at your European Economic Area in French, the order of the words is reversed, and you can see that in the attention, essentially. So that's cool. With attention, you can actually make use of all the states by having that focusing mechanism. And so people thought, if you can at each step decide which state you want to use, why do you also need the RNN cell to pass information between those steps? And that's essentially how transformers came to be. It's like people got rid of all the RNNs. So you see there's no arrow anymore between the tokens. There's no information that flows between them. But the attention mechanism makes sure that at each step, the model can attend to any token that it wants. And so you can, in addition to replacing the RNNs, now also the encoder block has an attention because it lost its recurrent ability. And that's like a very simple view of like how the transformer architecture looks like. And if you go to the paper, you see like that very complicated graph that I mentioned at the very beginning, but under the hood, you can think of it as like that simplified diagram. And as you dive deeper into transformers, more and more of these like steps gonna become more apparent, especially when we look at the anatomy chapter of the book. We're gonna see like what these multi-head attention mechanisms are, or yeah, that's and the input embeddings. But the crucial part is you get rid of the RNNs, you just use feed-forward networks, and you make use of that attention to capture like the sequential information. That is like one of the main ingredients that makes transformers so widely used, is that attention mechanism and these feed-forward networks that are way easier to train than recurrent neural networks. But there is a second thing, and that's transfer learning. And transfer learning is the idea that you can reuse a model that has been trained on some data on a new task. So let's say you go back 10 or even 5 years ago, the left-hand side would be how people would train language or models for like language tasks. You have some domain, maybe you want to do sentiment classification, you train a model on that, and that model is just used to make sentiment predictions. You have another domain, maybe you want to like identify names in a text. You would train a new model from scratch on that new task, and that model would just make predictions on that. The idea with transfer learning is that instead of just retraining or training a new model every time you have a new task, you can reuse a model several times. The idea is that you pre-train a model. In text, it's usually you train a model on like large amounts of text to, for example, predict the next word in a sequence of words or predict a masked word. And after you pre-train that model, you can use it for several tasks. And you don't need that much data anymore. So if you have a pre-trained model that's been trained on a lot of text and you want to fine-tune that, you want to train it on sentiment classification, you can do that with like just a few hundred samples maybe, and achieve like great performance. Whereas like before, when you had to train a model every time you had a new task, you also needed a lot of data to do it. And that's like the second aspect of transform models that made them so popular, that transfer learning works very well with them. And we're gonna see probably next time when we do like text classification, how that works like in more detail. So to wrap up kind of like where transformers came from, I thought we could have a look at like the timeline and how crazy it has been like just in the past 4 years now, or yeah, 4.5 years. It started with transformers. That's essentially that diagram I showed. That was like the first paper that showed that without recurrence, just with attention feed-forward networks, you can achieve like state-of-the-art performance in translation. They didn't think about transfer learning at that point, but it didn't take long, like half a year later or so, ULMFit came out, which was still a recurrent neural network, but they kind of cracked how to do the transfer learning. So they pre-trained a recurrent neural network on Wikipedia, and they showed that you can easily fine-tune that to do sentiment classification. And that was like the first time transfer learning really worked for NLP. Soon after, GPT came around, the very first version, which is like a model that's very good at generating text. Soon after, BERT, a model by Google, that's very good at all language understanding tasks like classification or question answering, these type of things. And that's like the first very popular model that was used to do NLP, bit transfer learning with transformers. GPT-2 was a model that came soon after, which was essentially scaling up GPT-1 and discovering that by just scaling up models, you can like improve their capabilities. That led to like a lot of like follow-up work in the past few years where people figured out that they're actually lost to that you can predict how well a model performs if you just make it bigger and train it for longer. And GPT-2 had like impressive capabilities when it came to generation. There was a famous example where you would feed a model that unicorns were discovered in the Andes, and the model would go on and generate a whole newspaper article about that story. And since then, you can see this is just like a subset of all the models that have been released in the past couple of years, but essentially every few months there is a new one, and we're going to look at a few of them in the book, not all of them. Some of them have like special architectures, some of them have been trained for longer or have been scaled up. But since then, the ball has been rolling quite fast. So that's it from my part for now. I'm gonna hand over to VB, who's gonna show you a little bit more applied how you can use transformers in practice.
All right, let me see if I can share my screen. Is it visible?
Yeah.
Oh, perfect. Oh, clicked on the wrong button. All right, so up until now, we basically went through like how did transformers came to be and what kind of what kind of architectures and what kind of findings and what sort of intuition led to the sort of architecture that transformers is. Now let's look at the transformers landscape, and let's look at how we can use some of these models without having to sort of go down into the trenches and just like test out how they work and what kind of applications can they help us out with, right? So when it comes to natural language processing, pretty much every task starts with a piece of text, right? In this case, I basically took the text from the book itself, which is a made up customer feedback. As you can see, it's basically, dear Amazon, last week I ordered blah, 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 sincerely, Bumblebee, right? And now what we're going to do is we're going to take this text and we're going to try and see what kind of different natural language processing tasks can we apply on this text to generate further insights from it. So I'm just going to quickly switch to a Colab notebook. Just a quick heads up, all of these notebooks as well as the Colabs would be available to you shortly after the session's over. So don't worry if you don't follow it fully just yet. You would get plenty of chances afterwards to go in. This is basically a version adapted from the code snippets used in the book itself. So if you've gone through it, you won't face much troubles. Just gonna quickly see if I can. All right. Oh, this is probably a bit too much. Okay, so again, we start off with the same text as we saw before. So this is a customer feedback, or some sort of a customer saying something to some sort of a agency of sort. Now let's basically take this text and now let's pass it through a text classification pipeline on transformers using the transformers library, and see what kind of a response do we get out of it. What's happening over here is we're essentially taking a text classification pipeline from the transformers library, and we're just passing the text to it straight up, without any without giving it any context of what sort of outputs do we want out of it, or and so on. So at the in the beginning, what it's gonna right now, what it's gonna do is it's gonna do sentiment classification on this. So it's gonna take this text, and it's gonna it's gonna give us one of the two outputs, either it is positive or it is negative, along with what's the probability of it being positive or negative, and so on. So we just instantiate the classifier, which is basically calling the pipeline, along with the text classification task. And then we just pass the text to the classifier, and we take the outputs out. So as we saw in the text itself, that this was a sort of negative text, as you can see from pretty much this this line, that the person ordered an Optimus Prime action figure, and well, they got a Megatron. Long sigh. So you can basically see that we did not really train a model for it, right? So we just used a language model that's available on the Hugging Face Hub, and we just passed this text to it, and without it seeing this particular example, this or examples of this specific type, it was able to give us a fairly reasonable output, which is negative, and also with a score of 0.9, and so on, right? Now that's just one part of it. We can also do all sorts of other things. So for example, we can also do named entity recognition, which is essentially sending the text and then identifying different entities from the text itself, right? So entities can be something like location, or can be something like date, can be a currency, or can be a name, and so on and so forth. And over here as well, what we're doing is we're from the same pipeline, for the task NER, we're instantiating named entity recognition tagger, and we're just passing our text to it. So again, just 2 lines of code, and we're passing our text to it. When we look at the output, you can see that it classified Amazon as an organization. Germany was classified as a location. Tron within Megatron, that got split because of the way it was tokenized, got classified as a person, if I'm not wrong, and Bumblebee got classified as a person as well, right? And again, keep in mind that this is just taking an off-the-shelf language model and then just passing the the text through it for the specific task. Then we can go one step beyond, and we can do some fancy things like question answering, right? Wherein we instantiate a pipeline for question answering, and we just we pass the text as context, and then we ask the question, what does the customer actually want, or what does the customer want in this particular regard, and it gave a pretty clear answer that the customer wants an exchange of Megatron, because they received Megatron and they wanted Optimus Prime, right? And all we did over here is we passed the text as context, which was the input text, and then we passed the question, and we passed it through the pipeline, the Q&A pipeline, and we got the following output, along with a confidence score. We can also do something like summarize long pieces of text and then summarize them into short snippets. So in this case, we instantiate a summarization pipeline, and we give it certain constraints. So for example, we want to take the 200 length sort of input, and we wanted to summarize it into a 45 length input. And let's see what the model comes up with. So the model basically says that Bumblebee ordered an Optimus Prime action figure from your online store in Germany. Unfortunately, when I opened the package, I discovered to my horror that I had been sent the action figure of Megatron. So, well, not too bad. It basically figured out the gist of what was there within the original text, and it still conveys the same meaning, more or less. And again, I just want to like emphasize the fact that you don't have to like you don't have to know a lot just yet in order for you to like play around with these pipelines. You can also just like, once you have access to this this notebook, or just go to the notebooks repository, you can pretty much just take any text that you get your hands on, and then just like play around with the pipelines, with the different arguments that they expect, and so on, and you can just from off the shelf models, you can get quite good results, and quite a good intuition of what's happening under the hood as well. Then now let's take the same text and let's try and translate it into German. So for this, we instantiate a translation pipeline, which is from English to German, and we specify a model for it, which was fine-tuned specifically for this task. And we pass it to the translator pipeline, and let's look at the output. My German's not that great, but from the very little that I know, it looks sort of okayish. It got quite a lot of words correct. At least I see Optimus Prime over there, and yeah, so it just worked quite all right, just from the text that we gave to it, using the model that we passed to it. Now let's try and generate a response to Bumblebee by generating some text. And so what we'll do over here is we'll create a prompt, which is, "Dear Bumblebee, I am sorry to hear that your order was mixed up," and then we pass it along to the model. And now let's see what sort of a response does it generate. So just for reference, this is the original message which Bumblebee sent to Amazon. Sorry, Amazon. And this is the response that our model created. So which is, "Dear Bumblebee, I'm sorry to hear that your order was mixed up. The order was mislabeled," which is very common. That's very honest, but I can appreciate it, because it was my understanding the day before your order, and so on and so forth. Well, I mean, like it does make sense from like a grammatical standpoint. We may not want to like share this verbatim with the customer, but the model pretty much like generated text which is sort of meaningful, and is also to an extent grammatical as well. So we like, if there was a language model fine-tuned specifically for customer service responses, then it would of course give a much better result than just using an off-the-shelf language model which is not fine-tuned for this specific purpose. So what we looked at so far was how we can, without writing too much code, how we can just like mess around with certain pipelines which are provided by the transformers library itself, and try out different tasks here and there, and see what the responses to that can be. I would encourage you all to play around with this as much as you can, and just try and break this, and like try to find edge cases, and then share them on the reading group channel on Discord, so that everyone can comment on that, and so on. One thing that you can also do from these models that later on when we go through like other chapters and so on, and in case you fine tune a model, or in case you come across one of these one of these pipelines and you want to share it with someone is that you can package these models into Gradio applications, which can then be shared with different people, and they can try it out as well. This can also be uploaded on Hugging Face Spaces. More on this in the next session. And as you can see, like what we've done over here is we just like create a very simple Gradio application. We just define an interface which takes this one question, question underscore answer function. And this question underscore answer function takes two parameters. Both are text types. So there is the first one is the context. The second one is the question. And we instantiate a question answering pipeline, and we get the output from it and return the output in output. So just with like 5 lines of code, you can create a decent looking application, which you can then use for all sorts of different text and so on. So let's try this out. I'm not sure if this still works, but let's see. So I'm just gonna give it some weird input. The customer wants happiness. The question, what does the customer want? Let's see if it still works. Oh yeah, so it does work. Like this was like fairly simple. I practically gave it the answer, but you can see that just with 5 lines of code, you can have like a nice UI wherein you can play around with your models yourself, and also you can share it along with your friends and with the community and with the reading group for them to test out your models and provide you some feedback, or just try it out for fun as well. So that was basically like a quick run through of what sort of some of the pipelines that you can use. There is a huge list of pipelines that you can oh, did I stop sharing? Sorry. Okay. I was trying to create open a new tab, but for some reason the Zoom thing is not letting me open it. But yeah, you can find out like all sorts of different pipelines that you can play around with in the Hugging Face docs. We can check it out in a bit. And yeah, again, I would encourage you to play around with it as much as you can, or as much as you desire. So I'm gonna head back to the slides real quick. So up until now, we've seen just a quick recap. So we've seen what sort of architecture sort of powers the transformer type models, and what led to it. We saw what sort of tasks, or like briefly saw some of the tasks that you can sort of do with these language models, or these models in itself. And now comes the big question that given the rapidly changing sort of landscape that we are in, wherein like there is a new paper every other week, or there is a new model every other week, how does one sort of build or like apply these architectures that are that are better than the ones that we saw in our pipelines, right? And this is like a fairly complicated topic, because you would first have to sort of like, the way you would go about it typically would be that you would implement this model architecture in some sort of code. So you would create either Torch, TensorFlow, JAX, or something like that. You would create a code base for it, and then you would first of all find the pre-trained weights that you can sort of import in this architecture, or like load in this architecture. And if they are available in the first place, that is. And then you would sort of recreate the way the authors of that paper sort of pre-process their inputs, and like pass them through the model, and then like whatever output you get, you would have to do some sort of post-processing on top of it. And then of course, like for fine-tuning it further, or for just like training it from scratch, you will have to define data loaders for it. You would have to define what sort of optimizer you want for it, define the loss function, and so on. So all of this can be like really, really daunting, just to be able to sort of apply a machine learning architecture, right? And not to mention, by the time you you do all of this, there would be another language model or another architecture already out there, and then you would do this whole thing all over again for that, right? And so how do we sort of deal with this? This is where the sort of Hugging Face ecosystem comes to rescue. So when it comes to the overall ecosystem, it's much more than this, but just to sort of concise the overall ecosystem, we have the transformers library, which basically has the code base of I think by now like hundreds of different models across like language, vision, audio, text, and so on. We have tokenizers for pre-processing, as well as like preparing the data for the to input into these models. We have data sets wherein you can carefully sort of version control as well as stream data from the Hugging Face hub. And then train a specific model that you want for your particular use case. And we also have the Accelerate library, which helps in certain optimizations in the way you train these models, right? And all of these sort of models, data sets, and metrics, and like everything sort of becomes a part of this Hugging Face hub, wherein you can sort of upload your models that you fine-tuned, or you can upload your data sets. You can do it, and if you want to share it with the community, then you can make them open source or like public, or you can also create private models, private data sets, and you can also use libraries like Evaluate to then like evaluate the predictions that you get from your models in a standardized format, and so on. And all of these sort of models are also well documented in the Hugging Face docs as well. Actually, let's quickly go and see these models real quick. 1 second. So this is how the hub pretty much looks like. So if you click on models, you can see that right now across different tasks and so on, there are 79,514 models. You can choose what sort of task you're looking for. So say, for example, you want to do say question answering, then you can click on question answering, and you can see that there are 2,400 models for it. You can then subset it. You can go back to the tag list. You can then like subset it on what data sets were they trained on, what languages were they trained on. So say, for example, if I click on German, then you can see that there are 12 models for question answering specifically for the German language, right? So you can pretty much like sort of slice and dice the amount of models that are available on the hub for your specific use case quite easily, right? You can also do across like different libraries. So if you want something which has TensorFlow compatible weights, then you can click on TensorFlow. If you click on PyTorch, then it would show up for PyTorch, JAX, and like so on and so forth, right? So this is models. Similarly, there are data sets. You can do the same sort of thing. So if you're for your particular use case, if you want to find a data set for a given task, so say, for example, we want something for translation, and we want something in, say, again, German, then you can see that just by this, we have data sets which have language pairs for German, and there are 47 of them, and you can basically like sort them, look at the most liked data set, look at the most downloaded one, and so on and so forth, right? So in general, like when it comes to when it comes to like fine-tuning your own model, or just like trying out different models, I would encourage you to just like check out models, and like for your specific task, just look at which model you can play around with first, and then just like pipe them into a pipeline, and then just like see how they perform in your for your particular data set, and then sort of look into fine tuning them, which we'll cover later on, and so on. And yeah, so it basically works out quite well in this case. Okay, let's go back to the slides. And then so now we've seen like how we can play around with these models, and like we've sort of looked at like at a very high level you know, how we can find different models and how we can find different data sets and so on. We haven't looked at, you know, much of code yet, but don't worry, we'll look at plenty in the upcoming sessions. But I just wanted to like spend like quick 5 minutes on the challenges that come along with using such models, right? So one of the first one of the first challenges is the language barrier itself. Majority of the research for transformers has been pretty much been in English language. There are multiple reasons for it. Like one of the biggest reason is that just like the data itself for like English language is available by truckloads. You know, like you can find so much in Wikipedia. You can find so much from Reddit. You can find so much from Twitter, and so on and so forth. Because like generally like communication across the world happens in English, so we just have so much data for it that a lot of research has been done in this language, right? What this means is that quite a lot of models are not really available for low resource languages, like for example Taiwanese, or say for example Latvian, and so on, right? There are like new multilingual models and so on, which are covered later on in the book, that help sort of solve this problem to an extent. But by and large, this is still a problem or a challenge. Next up, these models are data hungry. So even though we apply transfer learning, which reduces the need for a lot of training data, for a lot of tasks, you would still need like some training data. It's not that you can just do like zero shot, and zero shot meaning that you can just like throw any sort of data from any domain and then just like expect it to work. It still requires like quite a lot of data, which in most cases would you know, have to be either hand annotated or like have to be sort of processed in a certain way for the model and so on, right? So yeah, this is still like, this is also a challenge for these models. Next up is working with long documents. So the attention method in itself, it works well. We've seen that. However, it is a very expensive process. It is like from in like computer science terms, it is a big O of n square process. So meaning that you basically traverse the input twice. Oh, well, like each input, like each sort of token within an input with itself, like throughout, and that just means that computationally as well as like memory wise, this is a very expensive process. So this basically limits the length of sort of documents that you can pass through the model whilst it's learning, or whilst it's training and so on. There are now quite a lot of methods to sort of circumvent this entire problem, but it's not like completely solved. So for example, there are certain attention approximation methods like Nystrom approximation or something like reformer, which helps this case to some extent. But yeah, still like passing long documents is, you know, still an expensive process at the end of the day. Then, you know, as with like all deep learning models, these models are still black boxes to a much more extent. Like, you know, finding why exactly did a model make certain prediction is like, you know, and saying that with a cent% sort of accuracy is still not possible. So yeah, so this is also one of the challenges with it, as opposed to like classical sort of statistical machine learning realm, and so on. Last but not the least is the biases that these models sort of come with. Just the amount of training data that is passed to it has a lot of bias in itself. So there were like a lot of sort of discussion when GPT-4chan was launched, which was basically a model trained on 4chan. Is it called repos? No, like basically like 4chan sort of communities and so on, like all the text that was there, and it was just like spewing out really hurtful text and so on. So if you, it's still like these models still follow like garbage in, garbage out sort of principle. So whatever you put in the model would learn that, and whatever you put in would always have some sort of bias to it. So these models are riddled with these biases by and large. So yeah, that's basically it. When it comes to the challenges with transformers, we will address a lot of these in the upcoming sessions on like how you can sort of use different types of tricks or different types of architectures or different types of sort of pre-training methodologies to address some of these. But it's always good to know what sort of challenges come along with these architectures. Okay. So now we're at the end. I'm not sure, Leandro or Luis, if you want to cover the next steps.
Sure. So just to keep it brief, and that we have like a couple of minutes to answer a few questions. There's a link to the notebook, I believe, like in the first bullet point, so you can go to that notebook, play around it with yourself. There is also a Discord channel called Reading Group. In the role assignment channel, you have to ask for the collaborate role. And if you do that, then you get added to the reading group. And I think most of the organizational things we're gonna just post on that Slack channel, not Slack channel, Discord channel directly. We'll have some merch that we can give away, as well as some books. I'm also going to post a question about like access to books if you need that. Maybe we can organize something. And I believe Lewis has also posted the link where you can look at the book for free, at least for a few days. So I think we can now go over to questions, and I'm just going to allow anybody to unmute themselves if they have a question.
Hi, I have a question.
Sure, go ahead.
So hi, my name is Nicholas. I'm a data scientist at a nonprofit called World Quant University. And first, I just want to congratulate you guys on the book. Louis, Phoebe, Leandro, this is a great series. And I love the book. I love how applied it is. And I was very impressed as a teacher how you were able to get it all to work using Google Colab for people who want to get those resources. So like that was a very slick piece of programming that you all did, which I will definitely copy next time I teach a class that way. My question has to do with attention. So I understand that attention, you train attention by these masks, right? Which say like, this is the token you need to pay attention to. But my question is like, where do those masks come from? Like, are they kind of pre-trained, or like you're already telling the model where to pay attention to, or is it like, or is it kind of auto training where the attention should be?
Yeah, I can take that question. We're gonna look at that in much more detail in like one probably of the follow-up thing. There's the anatomy chapter that goes into more detail into how attention works. In short, it's like learned. So the model learns what it's looking for, and at the same time, it learns how to represent things that when it's looking for it, it finds it. And there's that concept of queries, which are essentially what you're looking for, and keys, which are the opposite. Like if you're looking for something, is that the thing that you're looking for? And these things are learned. So the model learns how it needs to encode questions when it looks for something and how it needs to represent the sequences that it finds it when it's looking for it. But everything is learned end to end, so it's nothing hard coded.
I'll let you unmute.
I think.
Yep.
Anybody?
Thank you, guys. That I understand. So it's learned. It's not hard coded. Got it. Thank you.
Sure. Any other questions?
Well, the reading group channel is already on, or you will set up one?
It should already be there.
So if you go to, are you part of Discord?
Oh, yeah.
Yeah, so I think in order to see the channel, you have to first go to the role assignment channel, and then you can select the emoji for collaborate, which is like the party face emoji. And then that should give you access to see the reading group channel.
Collaboration. Okay. Select that. Okay.
Maybe I can click it.
Yeah, that'd be great.
I already selected it.
So yeah, we're already almost there. So there's the role assignment channel. And you can see the collaborate, share, and ask for help. That's the role that you need. And so you need to click on that emoji, the party emoji.
I did it, but I don't see it. Still don't see it.
You don't see a reading group channel.
It should be under general.
Oh, now I got it. Okay, thank you.
Great.
Thanks.
Chris already ordered pineapple pizza.
Great. Really appreciate it. It's this book, it's so enlightening. I went through a few chapters, and before this book, I was reading some other NLP book, like the one by Juraski.
Oh yeah, really.
I mean, they are, they have a lot of good stuff, but they don't show you code example. But with the code example, I can understand much better. And you guys make it so easy. You can just one click, you can run it in Collab. Oh man, amazing. I can, insert some print statements and see, hey, how does this look like? What is this? What's the shape of this tensor? Or, a lot of time after you play around and, you insert some print statement, oh, you understand a whole lot better. Really appreciate it. Thank you so much.
Thanks. Maybe we have time for like one last question, because we're already a little bit over time. It's like, otherwise we also have plenty of time next session to answer more questions.
Hi, I wanted to ask, like general question, zooming out, that do you see like which areas are LSTMs, like things like LSTM, like pre-transformer models still, better at transformer, if any areas do you see in the application? Yeah.
You can take that. You trained lots of LSTMs.
It's been a long time ago, but I think there's still some fields like even in NLP where people find like that LSTMs for some very specific application they work quite well. But I think just the fact that the whole field moved to transformers is like kind of detrimental to LSTMs, because like it gets much less support than transformers, because now thousands of people are using transformers, all the libraries exist to train them and all the examples. So I think just naturally people use less LSTMs, but I don't think there's like a de facto thing where LSTMs perform way better. Maybe.
Yeah, I think there's a really interesting discussion actually between Jeremy Howard and other people on Twitter at the moment around, if you compare the total compute time of a transformer, so including the pre-training budget plus the fine-tuning budget, then things like ULM fit are much more efficient, provided you have enough in-domain data. So the idea is that, like, I think you used to train ULM fit from scratch at your old job, right?
Yeah.
And there, that took like a few hours or something. So the whole, that's pre-training, right?
Yeah.
So training ULM fit from scratch with pre-training is like orders of magnitude faster than a transformer. The downside is, of course, that if you want to do more sophisticated things like question answering or identity recognition, I think then it's a bit less flexible. Another thing I've seen used in practice is using LSTMs for compression. So if you want to, suppose you've got a super duper transformer like T5, 12 billion parameter model, trying to deploy that on like an edge device is going to be really hard. So what some people do is they take the model and then they kind of distill it into an LSTM. So you're essentially compressing the knowledge that you've gained and then kind of having a much smaller model. And depending on the task, this can be an efficient way of having something that is very good at language but is much smaller.
Cool. I think we're already like almost 5 minutes over time. Thanks a lot to everybody for joining. We will post more information on the Discord channel and looking forward to see you in 2 weeks.
Thanks, everyone.
Thank you. Bye-bye.
Thanks for joining.
Thanks.